Okay, I'm going to try to make this as quickly as possible. It's going to be tough. But imagine we have a little buggy here, a little car, and it's moving along at an initial velocity. And then it undergoes some sort of an acceleration, also in the positive direction, for a set amount of time. Um, what does that? So if time equals 0 at the moment where it begins the acceleration, but it was already moving, what are we looking at in terms of graphical representation? So first, again, let's look at our position versus time. Let's say that this spot right here is x. Oops. X equals 0. So at x equals 0, we end up with some sort of position versus time graph that looks like that. And then similarly, sorry, I'm trying to consolidate things here. If we look at our velocity versus time graph, I'm going to draw velocity in the red. We have an initial velocity, and it is going to accelerate away from that at a constant speed, so it's going to speed up. And of course, our acceleration versus time graph will look something like this, where this value is whatever that positive acceleration is. All right, the reason I want to go through this scenario is I want to talk about how we actually derive the equation to explain that in terms of velocity, initial velocity, time, and acceleration. And we're going to do that by actually starting with this line, the velocity versus time. And here's the piece that you need to understand, or that's important to recognize, is that calculus allows us to say that the area at any time interval under here, so if I start here and go to, say, here, for that delta t interval, the area under that line, the actual space occupied, is equivalent to the change in position experienced here. So whatever the area sums up to be in this triangle and this rectangle will be equivalent to the delta x in this direction. So how do you calculate that area? Well, I just kind of gave it away. We have a triangle and we have a rectangle. So let's start with the triangle first. So our delta x formula would be equal to the area of a triangle is 1/2 base times height. So 1/2, the base is going to be delta t, and the height is going to be the change in velocity from here to there, delta v, change in velocity. Now that takes care of the triangle. Now the rectangle is just going to be length times width. So again, length is delta t, width or height or whatever is going to just be our initial velocity initial. Now I'm going to rearrange this a little bit the way that we more normally see it written. 1/2 delta v times delta t plus v initial delta t. Now I had said before that we actually want this equation to be in terms of acceleration. So here's how we get to that. Delta v, change in velocity. How does it relate to acceleration? Well, remember that acceleration, or average acceleration, is equal to velocity final minus velocity initial over time. That's the same thing as saying is acceleration is equal to delta v over delta t. So if I rearrange that a bit, what that means is that delta v is equal to acceleration times delta t. And now I can take this and put it in here. And I end up with my equation of delta x equals 1/2 a delta t times delta t plus v initial delta t. So obviously we want to simplify that a little bit. So delta x equals 1/2 should keep the delta in there, a delta t squared plus v initial delta t. And there you go. There is one of our first kinematics equations that can be used to describe the change in position. Notice it's a quadratic, and so it corresponds to that parabolic shape.